we can use the colours of solution to analyse concentrations of species which are coloured. So now I'm changing from comparing solutions of different colours to thinking about solutions of just one solute. And let's think about red coloured. Okay. I hope you'll agree with me that if this is food colouring, the more food colouring you put into there, the deeper will be the coloration. And what that means is that if we had a light coming in on the other side, more and more of that light would be being absorbed by the particles that absorb the blue light. The higher the concentration, the more light is absorbed. The greater is the intensity, the more opaque is this solution. I hope you'll also agree that if I had this same solution in a vessel which was very, very wide, I'd be able to see through less of it. Simply, the more molecules that the light interacts with, the more of them are absorbed. And that can happen by increasing the concentration or by increasing the so-called path length, the distance through which the light travels before it comes out and is transmitted and reaches our eyes. So now, if I had, say, same solution, red, and one particular wavelength of red light passing through, this is 1 centimetre, this is 10 centimetres, less light would come through there, less of the red light would come through there than there. It wouldn't be the case that 10 times as much is absorbed in 10 centimetres than 1, because what's going on here is, let's say, for example, 1 centimetre absorbed 50% of the light, red light coming in, then this one would absorb 50% in the first centimetre. The next centimetre would absorb 50% of the residual 50% going through, so that'll be another 25%. The next centimetre would absorb 50% of that, which is another 12.5%, and so on. So in fact, we have a logarithmic scale. I'll just say now. In the analysis of concentrations of coloured substances I'm talking about, it's convenient to talk about the fraction of light that's absorbed of a particular wavelength at the colour of the solution. So the fraction of light absorbed of a particular wavelength I can think about as I naught. I naught is the amount of incident light of that wavelength, and I is the amount that's transmitted. If 23% was transmitted, then I naught would be 0.23 as to 1. And we have the relationship between the intensity of colour according to concentration and path length is that the log to the base 10 of I on I naught is minus ECL, epsilon CL. Epsilon is a proportionality constant, and it's characteristic of whatever the solute is, the absorbing species, at the particular wavelength. It'll change from wavelength to wavelength, but we're imagining one wavelength being passed through here. C is the concentration of the solution, and L is the path length. Let's just imagine some hypothetical values here. Suppose we had a solution in which epsilon was 10 in whatever units, and C, the concentration, was 0.1 moles per litre, and L, the path length, was 1 centimetre. Now we can work out from that it's not simple what the units of epsilon are. That doesn't matter from now. E times C times L would be 1. So we'd have the log of I on I naught is -1. So I on I naught 10 to the -1, which is 0.1, which is 1 to 10, 10% of the light of that particular wavelength would be being absorbed under those conditions. And so now, how do we do that? Oh, the bad news is that makes sense to me, and it might, I hope it does to you, but there's another way of looking at it. The way that chemists have traditionally done things, and you'll always find published if you're reading about this, they talk not about that relationship, but the upside down one. The absorbance, A, is the log of I naught on I, and that's plus epsilon CL. It means exactly the same thing. I just find that a little bit easier to visualize. The important thing is that the higher the concentration, the longer the path length, the more is absorbed, whichever way you think about it. So now, I have a solution of a particular substance. I don't know what its concentration is. I need to know. What I can do is make up a whole series of solutions of that stuff, of concentrations which I have made up and I know, and measure their absorbance. So I use those standard solutions. I know the concentration of this one has an absorbance. I measure that, and it's this. Solution I made up of this concentration, I measure its absorbance to be this. This concentration, absorbance this. This one, this. It's a linear relationship, the one we just had a while ago. There is the relationship. Now I get this solution and I measure its absorbance, and it happens to be there, that, then I now have analysed the concentration of that solution is this. So that's a pretty powerful way of measuring things. Now, I've got a little something to show you and to perhaps for you to puzzle about. Here I have a solution of a food colouring. I'm sure it's well and truly. And I want to have equal amounts, as close as possible, in each vessel. Looking good. Okay. So, there's no denying that they look the same, and I'll just use this video camera here to video from the top. I'll show you. So we have the same and the same, as you'd expect. They look the same, don't they? Now, the vessels are equal diameter and parallel sides. I'm going to add some water to one of them. And what do you think we'll see? Concentration will change, won't it? Which one? We'll do this one. There we go. The concentration in this solution is now less than in that solution. So when light passes through from the back into your eyes, or mine now, it interacts with less molecules here than here. So this looks less richly coloured, more faintly coloured than this one. It's absolutely consistent with Beer's law. And, oh my goodness. Let me show you what I've just seen. Not for the first time. I'll video this. So the solution on the right from here appears much fainter colour than the one on the left. We diluted the one on the right, previously exactly the same as the one on the left. I'm looking from above. To my eyes, I can't tell any difference between those two. They are absorbing light to exactly the same degree. Wow, interesting. When I look down from the top, I see exactly the same depth of colour, richness of colour. In other words, I guess I'm saying the amount of light coming through, it transmitted of this red light, is the same in both cases. How can that be? Think about it, and I hope you'll come up with an aha moment. Wow.